Hello there, my name is Manish Gupta. In this video, I'll talk about ranking in query auto-completion systems. In a previous video, I talked about ranking suggestions and the most common method for ranking suggestions as most popular completion. Right? So just to recap, in that video, I mentioned that wisdom of the crowd solution is the most popular completion-based solution. So you take all the queries in the query log, historical query log, and then index them in a try data structure. You also store the popularity values associated with those queries. So if a query was fired on the search engine 10,000 times, you would store that number along with the query in the try. When a user types a particular prefix, which is a partial query, let's say the user types AM, then you would figure out all the candidates from the try that match the prefix AM. For example, it could be Amazon, Amitabh Bachchan, American Airlines, and so on. And then you would rank them by the past popularity and show those ranked suggestions. While doing such ranking, you have to be also careful about doing language specific popularity computation, region specific popularity computation, and also decide what should be the query log aggregation period to compute popularity. It has been observed that for shorter prefixes, you could use a smaller query log aggregation period, but for longer prefixes, a longer query log aggregation period makes more sense. Also, you should give more importance to recent history compared to past history, and therefore time discounted number of impressions from history are more useful than caring about all parts of the history equally. Lastly, while ranking, not just impressions, but clicks could also be very useful. Clicks are much more confident signal compared to impressions. However, clicks are sparse, and therefore using clicks might be a good idea for shorter prefixes, but may not be that great for longer prefixes. Continuing from this discussion in the previous video, in this video, I'm going to talk about the following three important aspects of ranking for query auto-completion systems. First, I'll talk about traditional machine learning methods for ranking suggestions. Here, we will mainly talk about different kinds of features that may be meaningful in coming up with good ranking for suggestions in autosuggest systems. Second, I'll talk about convolutional latent semantic model, which was one of the first models, which was one of the first deep learning models for ranking in query autosuggest systems. Okay. Third, I'll talk about LSTM-based encoder system for ranking in QAC systems. Okay. So let's start with the first part, traditional machine learning methods for ranking suggestions. Here, I will discuss a whole bunch of features which could be meaningful in deciding the right ranking. These features could be based on the current prefix, the short partial query that the user has typed in so far, or they can be based on the suggestion features, the candidates that you want to rank, so their own features become important. Third, they could be based on the anchor query, the query that the user has, the query that the user just typed before this query in the current session. Fourth, they could be based on the entire session. So the user has probably been doing this session for quite some time, right? So if there are like 5 queries in the session, can I make use of the signals of those 5 queries so as to be able to decide the ranking for this particular partial query, right? Fifth, they can also be based on user features. So the user may be of a particular type, and therefore the ranking of the sessions should differ from user to user. Okay? Let's discuss these features in detail in this video, in this part. Okay? So what kind of prefix features can I make use of? The user might have typed just a few characters, and therefore I can actually use the prefix length in terms of characters as a feature. I could also make use of this signal if the currently typed prefix ends with a space character or not as a special feature. The space one, this feature makes a lot of sense because several times users tend to look at autosuggest results after an entire word has been typed. Uh, Several times because they're very fast typing users, so they don't really care about suggestions that come uh, when they're typing characters in the middle of words. But after a word, they tend to pause to think about the next word to be typed, and that is when they look at suggestion. That is why this is a very good feature to care for. The other features are more for different suggestions, the candidate suggestions. So you could use features like suggestion length, right? Frequency in the background set. So here background set just means the large query log that has been seen so far. So it could be frequency of this candidate suggestion in the past 1 week, 2 week, 3 weeks, 4 weeks, a month, or a year, different size of query log aggregation period, right? Whether the query is a navigational query or not, right? That could be a feature. Overall impressions of homologous queries. So what are homologous queries? Well, they use, we might want to show a particular suggestion, a particular query, the suggestion, but other queries with the same terms as the candidate query, but in a different order, are considered as homologous queries. Also, queries that extend the original candidate query are also called as homologous queries, right? So in general, you could sort of aggregate the impressions across all of those homologous queries and call them as impressions for this query. And lastly, you could also use another feature like number of queries with this suggestion as prefix. So specifically for queries which are localizable in nature, for example, car rental, you might want to care about also how many queries essentially exist in the query log which use this suggestion as a prefix. These are all nice, interesting features to care for. Very intuitive, right? The third kind of features are pairwise features, which have to do with the anchor query from session data. So the current user is in some session. So let's say the user has typed in 5 queries. So you take the previous query and call it as the anchor query. And the user is typing in a prefix for the current query. Right? So there is a candidate suggestion, and you want to decide where to rank this candidate suggestion. Pairwise features are going to be very meaningful in such a case. You would want this next query to be more or less related to the anchor query, the previous query the user has already typed in, right? So therefore, for each candidate suggestion, that you use this feature where you count the number of times you have seen the anchor query and the current suggestion co-occurring in the sessions in the query log, right? So that's one feature. Frequency of the anchor query in the query log or the background data is another feature. Also, edit distance between the anchor and the suggestion is yet another interesting feature to care for. Okay. Contextual features. So these features are the features which make use of a large amount of session data. So if the user has typed in, let's say 10 queries in their session so far, and this is the 11th query, then you might want to actually look at similarity between this current query and the previous queries in the entire session of the user. So you could basically look at similarity between this suggestion and the previous query, this suggestion and the previous 2 queries, this suggestion, the previous 3 queries, and so on. Okay. You could actually compute n-gram similarity, character n-gram similarity, or you could actually compute edit distance. So both of them can be used as good features. While typing queries in a session, users tend to reformulate queries. For example, if I type some query and I don't get good results, I try to type more specific queries. While doing so, I add a few words, right? Sometimes if my query was too specific and I don't get good results, I try to make it more generic to see if I get good results, right? By dropping some words. Sometimes some words need to be substituted, right? So that's called as reformulation of queries. Uh, in a user session, especially in longer sessions, tracking these reformulations is very interesting. What is the user doing across the session? Yeah. And then you could use features, a whole bunch of features by looking at various parts of this session. Okay? So, for example, by looking at the previous query and this query, I can actually check how many terms were dropped and use them as interesting features, or how many terms have been retained, how many terms were removed, substituted, right? I could also look at the entire session and look at all the words in the past few queries in the session and consider it as a bag of words. So how many of the words which are used in the current prefix are used from that bag of words? So number of used terms from previous queries in the session in which are used in the current suggestion. So you could use all of those as interesting features. Of course, as mentioned previously, you could compute cosine similarity between the current query and the previous query, or you could also compute other interesting features based on cosine similarity between the current query and the previous few queries. Right? You could use edit distance, and similarly, you could use edit distance just with respect to previous query, or you could use edit distance with respect to all the previous queries in the session in an interesting manner. Right? You could use just the query features like number of terms or average number of terms in the queries in the entire session, or you could also use this particular query number. So maybe this is the 10th query in the session. So the 10th thing is also important because you want to discriminate between short sessions versus longer sessions, right? Or is the user early in the session versus later in the session, right? You could use click-through data in the session. So if the user has clicked on previous queries in the session, when did the user click? So what is the average time duration between those clicks, right? Uh, um, so all of those are very interesting reformulation features to be used based on the current session data from the user. You could also use design features which are user specific. So for example, some users are too fast in typing, right? And they never care about looking at auto-suggest suggestion, right? Some users are slow. So you could use typing speed at this keystroke as an interesting feature. You could also use this feature, which is about users' history. So number of times a suggestion is actually issued by the user in the past. So it has been observed that users type the same query several times, right? So if the prefix matches one of the history suggestions, it's a very, very great idea to actually show that history suggestion from that user right at the top. Remember, this is personalized history for this user and not global history, right? On the other hand, you could also look at suggestion frequency over queries submitted by users of the same gender, right? So maybe this particular user's query log is too sparse. In that case, you could look at queries issued by other users of the same gender or same age group or from the same region also, so on. Okay? So you could also look at average length of queries the user has clicked in the past, average number of words in queries the user has clicked in the past, both in terms of characters and words. Right? Um, Lastly, you could compute similarity between the words in the current suggestion and words in previous queries in the same session. Like on the previous slide, we discussed, hey, you could use edit distance or cosine similarity, but hey, there are other kinds of distance measures, some of them semantic in nature as well, like wordnet similarity, n-gram similarity, or even word-to-vec kind of similarity that you could use for this purpose. So those were some of those features that could be leveraged in learning to rank kind of for traditional machine learning classifiers. In fact, this is yet another feature called as implicit negative feedback. So imagine a user who typed a prefix F, just F, right? And you showed a whole bunch of suggestions. Maybe the user is looking for FaceTime, right? And you showed Facebook right at the top. User paused for 2 seconds, right? Looked at all the suggestions, did not click on anything. They typed FA, right? User again paused for some seconds, right? And saw Facebook at the top, did not click on anything. Now, if the user is typing FAC, you should really not rank Facebook at the top. User has already looked at the Facebook suggestion for a few seconds and not bothered to click it. That's a great enough negative feedback to say that, hey, you should start showing some other suggestions now. Okay. So to incorporate this kind of intuition, you can design interesting features like maximum dwell time when a query is typed, total dwell time when the query is suggested, number of keystrokes at word boundaries, and so on. So there are several interesting user features that you could incorporate so as to encode this intuition broadly into a traditional machine learning model. Now, machine learning models can be trained in various ways to incorporate all these features for ranking suggestions. The most popular way is to learning to rank kind of models. For example, lambda rank is one of those popular ranking mechanisms which can be learned in combination with these features um, to rank those queries which were clicked higher compared to those queries which were not clicked. Right? So the idea is to rank those queries which were clicked higher compared to those queries which were not clicked and learn a lambda rank kind of a model using the features we just discussed. Okay, so this takes me to the second part of the video where we talk about a deep learning based model, specifically called as the CLSM or convolutional latent semantic model. With the increase in focus on deep learning in around 2015, people started using deep learning for query autosuggest systems as well. So in this particular method, the idea is to first take the queries in your query log so far and break them down into two parts, a prefix part and a suffix part. Thereby, you could mine tables of this kind, top one word suffixes, two word suffixes, three word suffixes. A few of them are shown here, but of course, you mine maybe a million of each, right? Million top one word suffixes, top two word suffixes, and so on. Specifically in this paper, they mined top 10K or top 100K suffixes based on their frequency, of course. Okay. So, and then the idea is that based on these prefix and suffix pair, right, which you have mined by breaking your by splitting your queries in the query log, you train a model, a convolutional model, which checks for the compatibility between the prefix and the suffix. So let me talk about the model first. So the model is a convolutional a neural network kind of model. So it takes a prefix and a suffix, these two things together, right? And it extracts trigram features out of these words. So you would have, let's say the word is architecture. So you'd get trigram, word trigram features, character trigram features, for example, ARC, RCH, CHI, HIT, and then ITE, and so on. So use those trigrams, and then you add a convolutional layer on top of it. So you have basically embeddings for those trigrams, add a convolutional layer on top of it, and there are more of those convolution and pooling layers. At the end, you basically get a 128 sized representation for your prefix. Similarly, you get a 128 sized representation for your suffix, right? And then finally, once you have those representations, 128 dimensional representations for your prefix and for your suffix, you would compute the cosine similarity and then say that, hey, train the model such that the cosine similarity for compatible prefix suffix pairs is high, and train the model such that the cosine similarity between incompatible prefix and suffix pairs is really low, right? So the model is trained to maximize the cosine similarity between compatible prefix suffix pairs and minimize the similarity between incompatible prefix suffix pairs. So that is how essentially we train this convolutional latent semantic model. Now at test time, what do you do? So at test time, when you get a prefix, you basically extract p bar, which is basically removing the partial last word. Right? So essentially, when the user is typing in a prefix, maybe the user has typed in cheapest flight, FRO. So you would take just the cheapest flight part, right? You would then try to combine it with any of those 10,000 popular suffixes or 100,000 popular suffixes, as the case may be. I mean, you can keep a list of 10,000 or 100,000 and try to combine it with all possible suffixes. Right? And then, whichever suffix basically gets the highest cosine similarity score from your CLSM model is going to win, and you would show it at the top. Right? So, for example, if the prefix was what to cook with children with chicken and broccoli, and you would show bacon at the top, noodles, and so on. So all of these make quite some good sense. So they all seem to be pretty good suffixes. Right? Similarly, if the user has typed in cheapest flights from Seattle, you would show DC, Washington, DC, Bermuda, and so on at the top. Now note that sometimes it could lead to nonsensical suggestions. For example, cheapest flights from Seattle to airport doesn't make too much of a sense. But if you look at it, most of these are suggestions otherwise are pretty reasonable suggestions. So that was about CLSM. Now let's talk about yet another interesting model for coming up with for ranking suggestions in QSE systems based on LSTMs. Okay, so the idea is that you want to show good completions. So if the user has typed in cheapest flights from Seattle, right, you would want to typically show cheapest flights from Seattle to Vancouver and not show bad completions like cheapest flights from Seattle to airport or cheapest flights from Seattle to study and so on. You want to, of course, avoid those, but show things of this kind or share things of this kind. Yeah. Now, to be able to learn such good ranking models, you first need candidates that could be proposed, right? And then you would want to ensure that they get a very good click-through rate, right? So you want to train a model such that it can rank those candidates which have a good language modeling score, right? As well as they are promising candidates from a clicking perspective. Okay? So accordingly, these folks basically proposed um, in 2020 an interesting model which does candidate generation and candidate ranking. The ranking is done using an LSTM based model. So this LSTM based model has two main components. Of course, one is an LSTM. So using a large query log, you basically train this LSTM part from a next word prediction kind of a scenario. So you say startup suggestion, and that generates the word research. You say next word research, and then you should be able to generate scientist. Say scientist, and should be able to generate end of suggestion. So the idea is to be able to learn a very good language model based on historical query log. So that's the first part of this model. The second part of this model is to basically take these generated tokens and combine it to form a suggestion. And finally, on top of this, come up with a learning to rank layer, which ranks those suggestions higher, which were clicked, and ranks the suggestions which were not clicked lower. Okay? Of course, clicks or not clicks are labels which are available in your training data. In the past query log, you do know which suggestions you showed and which of them were actually clicked. So those which were clicked, the model is trained such that it is supposed to rank those suggestions which were clicked higher and those which were not clicked lower down. Okay. So in that sense, is this particular model uses two kinds of losses. One is the language modeling loss, and the other is this ranking loss. Now, there are other systems which you can compare this model with. For example, you could compare it with the most popular completion. You could compare it with the maximum content generation, which is basically using n-gram word tries to be able to generate suggestions. You could also compare it with the CLSM method that we just talked about, right? The last word generation by looking at 100K most popular suffixes, most frequent suffixes. So if you compare, the method, what you see is the baselines compare as follows. People typically do these comparisons on AOL data. So AOL data is this infamous data set about the AOL search engine, which was made public somewhere in late 2000s, right? So I think somewhere around 2007, 2008 time period, right? So that query log is publicly available still, and people use it to compare autosuggest systems on this publicly available data. So what you see is the metric recall at 10, which basically says higher the better. So what you observe is that among these systems, the most popular completion system, the MCG system, the n-gram word tries based system, and the last suffix prediction system, you observe that the n-gram word tries performs better on all kinds of prefixes, seen prefixes as well as unseen prefixes. So unseen prefixes are prefixes which were not seen in the training part of your data, right, or on the past query log. Yeah. Compared to that, the proposed normalized language model system. So this is basically normalized or unnormalized language model. So you could use language model, and then on top of that, there is of course a learning to rank layer. So whether you use normalized or unnormalized shows you that hey, the latency of your normalized model is pretty high. So therefore, they basically mention that this first part, which was actually trying to learn a language model, is an unnormalized language model, so as to have pretty low latency, 3 milliseconds. But let's see how does it compare in terms of accuracy. So in terms of accuracy, here the metric that they have used is called MRR at 10. So MRR metric is called as the mean reciprocal rank metric. Mean reciprocal rank metric. Now, that metric basically says that let's say you showed 10 suggestions to people. And if the click suggestion was 4, then MRR is 1 over 4. If the click suggestion was I position, then the MRR is 1 over I. Okay, that's how MRR is computed. So MRR is a value between 0 and 1. And of course, it's nice if you have 1 as your MRR. And you compute MRR across various queries, and then you average out MRR across all of them. Okay. So again, they report it for seen and unseen prefixes separately. And as you observe, you know, uh, the proposed model, which basically does normalized language modeling, plus it basically makes use of this learning to rank click-through rate loss, and it also makes use of frequency of impressions. This model gives you the best results, not just across seen prefixes, but also for unseen prefixes. Another interesting observation is that whether you use unnormalized model or the normalized model, there's not too much of a difference in the results. The results are pretty similar. And therefore, to save on latency, clearly you would want to use the unnormalized model. Right? That gives you good results as well as saves on latency as well. So that's that. That's basically a quick discussion on traditional machine learning and some deep learning methods for ranking in QAC systems. So there's a summary. We discussed three things in this video. One, various features for traditional machine learning for ranking suggestions. The most popular learning to rank model is lambda-mart model. Okay. Then we also talked about two deep learning methods for ranking suggestions in QAC systems, specifically a convolutional neural network-based method called as convolutional latent semantic model. And then we also talked about an LSTM encoder-based model, which was trained on two different loss functions, one for the next door prediction and second on the click-through rate prediction. So predicting which queries are more likely to be clicked. Okay. So thanks for watching. If you would like to connect with me, here is my LinkedIn and here is my homepage. Thanks so much.